So in this video we are going to talk about brushless DC motor. What is so special in brushless DC motor? That first of all, for understanding the operation of brushless DC motor, we must understand what is brush DC motor. The problem with brush DC motor is that mainly coming from commutation, and another problem is that field winding losses. Because ohmic loss takes place in field winding, but the problem with brush DC motor is that it actually demands a very what to say kind of uh, it demands a kind of you it's like it requires that mechanical contact, and due to that mechanical contact there is a continuous uh, means degradation of that brush health with time, and therefore you need a periodic maintenance. You need to replace the brush at a regular interval. Yes, you can take care of the commutation process, you can go for an advanced design that will reduce the sparking of that commutation teeth, but you cannot avoid sparking, and also that limits the current, and also this kind of arrangement is not good, means it's not a very like compact arrangement. So what we need is that a very simple thing, that is the means some machine that somewhat invites the feature of our DC machine. At the same time it makes or means it is free from the shortcomings or drawbacks of DC machine. So first, the and foremost drawback of DC machine is its that problem with its commutation. Another problem of DC machine is that here is its field loss. So what would happen if somehow we can replace, DC machine is a kind of double fed structure, double fed magnetic system where you need field or armature both to be energized. Now if you replace one part by a permanent magnet, then either the rotating part or the field, then it can reduce the cost. Now, which electrical machine is characterized means or having characteristics quite close to your DC shunt machine? If you think, you will find the AC three-phase induction machine. Now, how we think about BLDC, that if we can drive our means induction kind of machine having feature of or means driven by DC supply, or means powered by DC supply, and also free from that brush case. So people conceive the idea of brushless DC machine. The stator of these are identical to a conventional induction motor. The stator core, actually this diagram is slightly misleading. It should be filled with some structure, like this is the whole stator core. I take images from the book because so it can reduce some of my time, because already due to my health condition I lost some important time. So I just take. So you can understand this is that Here it is like the case. Now see what is happening, that this gives us a stator core that can generate very high, means identical to our induction machine, and similarly like induction machine it is made up of that means silicon steel. And these are the slots, status slots here. Due to my means when I just try to color to make the core more clearly visible, I just over means put some color on this also. These black ones are the means your armature conductor, just like a normal induction motor stator winding. Now armature is made up of permanent magnet, and the rotor core is mounted on shaft. For successful commutation, now who will do that commutation? Here the principle is that you take a DC, then you feed it to your power electronics converter, that will generate a three-phase AC supply. That three-phase AC supply you are going to feed in this stator winding, and that stator winding will produce a rotating MMF at synchronous speed, and due to that means magnetic interlocking with that synchronous speed, it will start rotating. Now here now we need for successful commutation we need rotor, means feedback from our rotor, and that is why we commonly use Hall sensors. Two different kind of structure we can have. One is, this is a surface mounted permanent magnet motor, and this is interior permanent magnet motor. Now they are having their own advantage and disadvantage. This is actually, this gives the rise of projected pole, while this makes the surface, the outer surface, smooth cylindrical shape. But do not get confused that it is same as cylindrical rotor machine. In fact, if we compare the material characteristics, we will find this actually offers, magnetically it offers more saliency than this one, surface mounted one. I would like to mention one thing, that saliency doesn't mean how much projected poles are, how much means what is the, means like what we understand by the what saliency is, that if we have a projected pole structure like this, like in this case, so we understand the amount of saliency means how much it is, this pole head is and the difference between the this distance we consider as the amount of saliency. But saliency has nothing to do with this. Saliency is something that is the difference in your reluctance offered by two means extreme path. Extreme path means in one where the magnetic flux will face minimum amount of reluctance, and another path where the magnetic flux face the maximum amount of reluctance, and this difference is known as saliency. Now, how you will create it? Generally, in case of synchronous machine, what we understand that by means of air gap we used to create it, but that this air gap and variation of air gap, it is also this. If you think about air gap, you need space. The machine will become bulkier. So, if you want to reduce the size of the machine, the new machine must be compact, because you are going to use this machine in some inside some say your vehicle or somewhere. So it is not good that you use it that way. The main advantage of this BLDC motor is that what I have some interest in small scale machine. What I found that in case of mainly for very small scale submersible application, most of the machines are BLDC machine. Like in your aquarium, if you want to deploy a filter that is used to clean the aquarium water, you will find there is a submersible water pump and it is made up of BLDC machine. So those things, because this deploys a solid state commutation and it has got nothing to do with physical commutation, and physical commutation, physically it's permanent magnet, so you can do it as per your requirement. Now the most important part of this, so if we see this one, see this is a brush DC. What is happening? This is very beautifully shown here in this presentation. You can see there is a sparking every time a commutation is taking place, and then what happened in case of brushless DC machine? Try to understand. This is a very interesting things that rotating MMF is being produced by these poles, and they cause it, making it rotation in this direction. Now the only question is that how is as of now what I have discussed, it makes you a bit confused that then which one to select. It's like that your stepper motor, synchronous reluctance motor, and now this brush DC motor, and how different they are from each other, and how much they are similar, right? Permanent magnet brushless DC motor. You can see here it is the stator winding, then there is stator frame. At the end of this rotor, there is Hall effect generators that will be we use Hall effect generator to sense the rotor rotation, and there is permanent magnet rotor and also ball bearing. Now the stator rotor we already discussed it. Now how it works? See, the rotor and stator of a BLDC motors are as shown. Now BLDC motor is the rotor is a permanent magnet one. The stator has a coil arrangement. The internal winding of the rotor, we have, out of these three coils, only one coil we will be considering here for simplicity of understanding. If you are not getting this, I would like to show you this one. Which one? Yeah, you can see this. This is a case that how brushless DC motor works. This red and green indicating north and south. Now the question that may haunt you, that isn't it very similar to that stepper motor or your like your that switch reluctance motor? In this context, I would like to make you understand, or means let you understand one thing, that in case of switch reluctance or in other motor, what you have it happening, that it is uh, merely one or two phase, and it was due to DC that field was produced. It was switching of DC, and here it is also switching of DC, but the DC is switched in such a way it produces a three phase alternating current, and we are ensuring a flow of three phase alternating current through our machine winding. So basically, it is identical to that rotating MMA produced by a three-phase machine stator winding. Similarly, here also we are giving a pulse. Now, unlike that, means pure sinusoidal pulse, which is common, or means wave, which is common in case of a three-phase alternating current machine. Here, it may be the case that it is a pulsating wave, means the inverter cannot produce you a pure sine wave, that is difficult for the inverter. So it may happen the inverter is giving you more or less square wave. Generally what we did, what is being sold to us as a sine wave inverter, it is not the switching action that produces sine wave. Whenever there is a switch, it will always produce a square voltage, but then we apply some filter and other kind of mechanism to just try to remove the harmonics and make it look like more or less a sine wave. That is what we do. Now in brushless DC motor, what I was trying to make you understand, that unlike the synchronous or switch reluctance motor, this is the not due to a phase interaction, rather this is it is in other way it is somewhat misleading also, but it is also giving you a better understanding. That is why I take this diagram. Here in brushless DC motor, all the phases are generally energized and they produce a rotating MMF, and that rotating MMF causes your machine, or means magnetic interlocking, just like that synchronous machine, and it rotates, right? So that is the case here. Now Hall sensor is means to understand the rotor position, Hall sensor is like an inevitable option. So let us understand what is Hall sensor. When a magnetic field applied to a system with electric current, a Hall voltage perpendicular to the field and current is generated, and this was discovered by Edwin Hall in 1879. Here you can understand what is happening. This is stator winding. We are taking the side view. This is the rotor magnet, and there is a Hall sensor, and Hall sensor's magnet. So when it rotates, this Hall voltage will be sensed to understand that what is the here. Now here is a just a side by side comparison between BLDC and brush DC motor. So in BLDC it is electronic communication based on Hall position sensor. In brush DC motor it is brushed communication. Maintenance, obviously BLDC almost maintenance free, while brush DC leads periodic maintenance. Life expectancy of BLDC is much more much longer than that of brush DC motor. Speed torque characteristics, BLDC offers flat characteristics, means enables operation at all speeds with rated load. But what we observe in case of brush DC motor, if we increase the load, it is not totally flat, it is more or less flat, but there is means speed regulation occurs. Efficiency is very high. nearly means above 90%, and for brush DC motor it is means you can make it as high as 80%. In real case it is within 80 to 90%. And if you are not machine is not under maintenance and need maintenance, then it can fall to 60% also, or means if you do not operate near optimal point. So now if we consider torque volume ratio or torque inertia ratio, in case of BLDC motor it's very high, but in case of brush DC motor it's quite low. So if we need compact application, we should go for BLDC motor. So all these are advantages of a BLDC motor, as well as its speed can be higher than the brush DC motor, because in brush DC motor higher speed means you need more advanced commutation technique to make things happen, but in BLDC motor the commutation is done through electronic switches, so therefore it is almost free from that hassle of means sparking cross brush. Now here it is, the cost of this is very high, while this is having a very low cost. Control circuit is very complex and expensive, and also closed loop. Try to understand, because every that commutation, whatever it takes place based on the rotor position. Now in case of this one, it is not done in that way, and this is just difference. Now let us go and understand the main working principle once again, and let us find out some empirical equation for BLDC machine. So now what is in this BLDC square wave we are considering? Actually, I hope you know in inverter you must rate 180 degree and 120 degree mode of conduction. So in BLDC square wave we will go for 180 degree mode of conduction, right? So typically there are two modes we can have. One is 180 degree pole arc and 120 degree current sheet, and another one is just alter change this 120 degree pole arc and 180 degree current sheet. So first let us consider the BLDC square wave motor with 180 degree magnet arc. This is what I just show here. You are having a PM BLDC. Now one means a cylindrical motor. One half of the motor is north pole, another half of the rotor is south pole. One half of the rotor is north pole, another half of the rotor is south pole. Now here we are assuming the coils are full pitch and has n turns each. The slot pitch is 30 degree. We are having 12 number of slots, so slot pitch is 30 degree. And we are considering that single layer winding is used. Now if we neglect fringing, the air gap flux density will take what type of shape? The air gap flux density will take, if we do not go to much complicacy of different type of flux wave that I discussed in my last semester video, fundamental of rotating machine, you will get this kind of square wave type of air gap flux density, right? And for that air gap flux density, it is just like that. Even in case of explaining DC armature reaction, we means we saw this kind of flux linkage of a particular coil. So flux linkage of a particular coil, how we can write the flux linkage of R1 R dash, that we can write using a function of theta. What is the value of maximum flux linkage? So flux linkage, we are having flux linkage is undergoing linear variation. What we can write that the EMF induced in that so this d theta dt can be replaced by omega, that is the angular speed, and furthermore we can write it like 2 into 2 pi psi max omega. Now if you put the value of psi max omega, you will get, it will give you 4 R L B G in omega, right? The EMF of induced in R2 dash, this is R1 dash. What about R2 dash? This will just be shifted by same magnitude, but will be reduced by a factor of 30 degree. So now if these two coils are connected in series, the phase voltage will be how much? The phase voltage will be where your NP is equal to 2 into N is equal to of turns per phase, right? Now the EMF and current waveform would be what? This is our EMF waveform will be, this is E R1 R1. What about E R2 R2 dash? There will be just a 30-degree difference. So what about ER? You will get them by adding them. So you are basically getting 150-degree size of your ER. Now what about IR? IR is means higher, what we are getting, it's 120-degree. Similarly IY is another 120-degree and I beta is another 120-degree. Like we are having, means we just break the current in this 120-degree mode. This is which one? This is the first mode, that is 180-degree pole arc and 120-degree current shift. Next we will see 120-degree pole arc and 180-degree current shift. Now it is also very clear that at any instance it is two phases are carrying the current. At any instance, this is the beauty of 120-degree conduction. Only two phases are carrying the current. Like here, if you see which two phases in this way, in between this, you can see the here till this point. What I am trying to say, in this zone, you can see it is only IY, IB. They were conducting, but IR was 0. But once IR becoming high, then what happened in this region? IR and IY is conducting, but your IB is 0, right? Similarly, in every instance only two phases are conducting. So the power equation will be how much? This is the amount of instantaneous power. Now we can write from the EMF equation. This is our total EMF for a particular phase. So the power equation will be how much? It will be the torque equation will be how much? P will be P by omega, right? Now in this P by omega is equal to 2 EI by omega. Now this 2 EI by omega is what? This 2E is actually is equal to your this one. So your torque equation will become 4 R L B G N P. Omega is not here. So into I. The torque is taking the same form as your DC machine case K phi I, and you are having E is equal to K phi omega. What is your phi? Phi is your this BG RLBG. This is your phi, right? Now here we can see a very interesting things that how switching, this is the circuit. So clearly S1 and S4 are with phase R. Let me draw it. Where is that pen? Yeah. So S1, S4 are with R. So this is your R, right? This arm is for Y, and this is for your blue. So now let us see that what is happening here is when we are at the first 0 to 60 degree, S1, S6 all are off. So what you are going to turn on at this instance, it is your is which one is 3 and is 6. Similarly here, which one you are going to switch on is 4, and that other one, that is plus, is 3. Then in the next instance it is S4 and is they have made it, sorry, it is S2. This one I read it incorrectly, it is S2. So this is S6 and this is S3. Here it is S3. This one is S6, S5, S1, S4. So S3. Now here it is S1, S1, and these two be S5, S5. So together if you consider their total conduction time, here it is again S6. In a span of 360 degree, you will find all of them have got a chance to conduct for 120 degree. So just like that 120 degree inverter, it is 120 degree conduction mode. And so here we are getting this kind of current, that is for 180 degree pole arc and 120 degree current mode. Now what we can do here is that we can just try to realize the other concept, that is our 180-degree current mode and 120-degree phase shift. So same sequence, just here you can God. Yeah. So see here what we want 180-degree conduction. So how it could be achieved? Here, if we are talking about the sequences, then it should be like this one. So clearly you can see that one switch is continuously on for 180-degree and the other switch is continuously off for 180-degree. Now interestingly, here in this and also in the previous one, you must have noticed, I just deleted that, just a minute, let me insert it. This was in that case when we are talking about 120-degree, it was the switching interval and our phase currents, right? Now here it is somewhat different. What we are writing? We are writing that rotor position. So why rotor position? It is 0 to 60-degree, that is so important here. Try to understand that when you are developing a particular current, it produces a field and that gives you a particular shift. So these DC source 180-degree if we want, then what it should be? The first half cycle all the time T1 should be on, right? Here actually you can see this. This is the scenario, that how the things should be and in which way it is also given, like T1, T6, what should be the means way you should toggle your switch, that is given. Now the last thing that remains, that is this one, that is 3-phase 3 pulse and 3-phase 6 pulse BLDC stator. Now in order to understand this in a simple manner, we can go back to our narrow spread stator coil and wide spread stator coil. What was there in narrow spread stator coil and wide spread stator coil? In narrow spread, it was for every part you are having plus minus, and for wide spread stator coil you didn't have that plus minus. In narrow spread you are plus one phase, the negative of that phase, then say A dash, B dash, C dash, it was like that, narrow spread coil. But in case of wide spread, how it was? It is like all the 3 A, B, C phases are there. Now here you can see that what we do in that three-phase, three-pulse BLDC motor, we are going to apply three pulse. Then the question is that how this can produce means the waveform that we want. It is very simple, like it was in your three-phase three-pulse case. It is just like, just let me write. I need some time because this is something I have to think and write. So what was in the case in for widespread coil? It is like first 120 degree you allow flow of certain coil. Then after that, now here in this continuous case, the question is that how you can realize it, because it is steady, right? So just let me write, then I. So here, instead of discussing that, let us try to understand what would happen in case you have a three-pulse one. Clearly, this is not for three pulse, but in case of three pulse, what you need to do is that this is your RYB phase winding. Clearly, your winding will be like embracing 120%, 120 degree of your total stator arc, like that in widespread coil. Say this is your R, Y, and this is B. Now clearly they cannot means how you can connect them. Obviously your objective is to make your PMDC rotate. Pole arc can be different. Pole may not, pole arc to pole pitch may be different, but clearly that phase winding should be in that way. Now when you need to produce, say you want to produce north south, how you need to how can you produce north and south? Say this is here you are having south and north. Basically but strange thing is that here all this is in terms of DC. How you can switch the DC to make it happen? That is the biggest question. Only way is that if you want to orient them in this way, you have to switch the pulses in such a manner, in plus and in minus, that they form this kind of structure. They give this kind of means rotation. Obviously this will give you a higher degree of freedom which this cannot give, but it is also a possible configuration for our machine. These BLDC machines are finding their applications in many places. So now the obvious question, and that is the last question that we should find answer, that what is the shortcoming of BLDC? Is there any shortcoming, or BLDC is totally full of advantages? So first, once again, before we conclude, let us quickly visit the advantages. Advantages is that no load current is low, and also maintenance free. There is no torque is required. Only thing is that like only drawback is that it's as of now what we studied, it gives us an impression that it is the cost of the BLDC machine that is only the negative thing. But uh, is it the only one, or it has some other like other disadvantages? Another technical disadvantage, that is economical point of view, technical disadvantage when brushless DC motor is operated at low speed, then there are slight vibrations occur during low speed location. Why this vibration takes place? Because there you are means trying to reduce the speed of this induced EMF, means speed of this rotation, by reducing the frequency, and at that time it is difficult for means like if it very fast, then your motor won't vibrate, but if it is very low, there is a chance that due to that residual magnetism and other factors, I am not going to that technicalities on that, because that would means take a large amount of time for me to explain you. But in low speed BLDC vibrate. Even if you want to test, you can take any small aquarium pump or any other pump and apply subnormal voltage. You will see that it will start vibrating. But the danger is that if this natural frequency of vibration match with some other vibration of the body or plastic parts, then a resonance may occur, and we all want to avoid resonance as much as possible, because only in filter design or some selective circuit resonance play a great role, but otherwise it is totally a disaster. So mainly technical issue, economical issue is costly, and technical issue is that resonance may takes place, and so we may look for a PMSM motor.